Chapter 1.4.1 Pods. Pods in Kubernetes are the smallest deployable units of computing that consist of one or more containers with shared storage and network resources. They are co-located, co-scheduled, and run in a shared context. Pods serve as application-specific logical hosts and can include init containers for startup processes and ephemeral containers for debugging. In non-cloud contexts, pods are similar to applications running on the same machine. What is a pod? To run pods in a Kubernetes cluster, a container runtime needs to be installed on each node for the pods to run. A pod consists of shared Linux namespaces, C groups, and other isolation features that isolate containers within the pod. Pods in Kubernetes are used in two main ways: running a single container per pod or running multiple co-located containers that need to work together. The latter case is for tightly coupled containers that form a single cohesive unit. This grouping of multiple containers in a single pod is an advanced use case and should only be used when containers are tightly coupled. Replication for resilience or capacity should be managed through workload management rather than running multiple containers within a pod. Using pods. The provided text explains the concept of pods in Kubernetes, specifically focusing on creating pods using workload resources such as deployment or job instead of creating them directly. Pods are used to run a single instance of a given application and can be scaled horizontally by using multiple pods, each for a different instance. Replicated pods are managed as a group by a workload resource and its controller, which helps with application scaling and auto-healing. Pods provide shared networking and storage resources for their containers. It is recommended to refer to the documentation on working with pods for more information on how to effectively use pods in Kubernetes. Working with pods. Pods in Kubernetes are not typically created directly by users, as they are meant to be disposable entities. A pod is scheduled to run on a node in the cluster until it completes its execution, is deleted, evicted for lack of resources, or the node fails. The name of a pod must be a valid DNS subdomain value, but this can lead to unexpected results for the pod hostname. In terms of the operating system, Kubernetes currently supports only Windows and Linux, which can be specified using the .spec.os.name field in v1.25. Controllers such as deployments, stateful sets, and daemon sets manage multiple pods, handling replication, rollout, and automatic healing in case of pod failure. Workload resources use pod templates to create and manage pods, with controllers ensuring that the running pods match the current pod template. When modifying a pod template or switching to a new one, the existing pods are not affected immediately. The workload resource must create replacement pods that adhere to the updated template. Different workload resources have their own rules for handling changes to the pod template. For example, the stateful set controller ensures that all running pods match the current pod template. If the stateful set is edited to change its template, new pods are created based on the updated template, gradually replacing the old pods. The kubelet on nodes does not directly manage the details of pod templates and updates, as these are abstracted away for system simplification and extensibility without changing existing code. It is essential to understand these concepts to effectively manage and maintain pods in a Kubernetes cluster. Pod update and replacement. When updating the pod template for a workload resource in Kubernetes, the controller creates new pods based on the updated template rather than modifying existing pods. While it is possible to update some fields of a running pod directly, operations such as patch and replace have limitations. Most metadata about a pod is immutable, including namespace, name, UID, and creation timestamp. The generation field must have values that increment. If a deletion timestamp is set, no new entries can be added to the finalizer's list. Changes to a pod's image, active deadline seconds, or tolerations are permitted, with restrictions on the types of updates allowed for the active deadline seconds field. Resource sharing and communication. Pods in Kubernetes enable data sharing and communication among their containers. Each pod can specify shared storage volumes, allowing all containers within the pod to access and share data. This also enables persistent data to survive in case a container needs to be restarted. Each pod is assigned a unique IP address for each address family, and containers within a pod share the network namespace, including the IP address and network ports. Containers within a pod can communicate with each other using localhost, standard interprocess communications, or IP networking. Containers in different pods have distinct IP addresses and cannot communicate by OS-level IPC without special configuration. Additionally, containers within a pod see the system hostname as the same as the configured name for the pod. For more information on how Kubernetes implements shared storage and networking, you can refer to the relevant sections. Pod security settings. The security context field in the pod specification allows for setting security constraints on pods and containers in Kubernetes. This field provides detailed control over permissions, such as dropping specific Linux capabilities, running processes as non-root users, setting SEP profiles, and configuring Windows security options. However, caution should be taken when enabling privileged mode, as it can override other security settings. In Kubernetes 1.26 and later, Windows containers can also run in a privileged mode by setting the Windows options.host process flag. Additional information on security constraints for pods and containers can be found in resources, such as Linux kernel security constraints for pods and containers, and configure a security context for a pod or container. Static pods. Static pods are managed directly by the Kubelet daemon on a specific node, without the API server observing them. The kubelet directly supervises each static pod and restarts it if it fails. They are always bound to one kubelet on a specific node. The main use for static pods is to run a self-hosted control plane, where the kubelet supervises individual control plane components. The kubelet automatically creates a mirror pod on the Kubernetes API server for each static pod. Static pods cannot refer to other API objects in their spec. Pods with multiple containers. Pods in Kubernetes are designed to support multiple cooperating processes that form a cohesive unit of service. They are automatically co-located and co-scheduled on the same machine, allowing containers to share resources, communicate, and coordinate termination. There are two main ways pods are used in Kubernetes: running a single container or running multiple containers that need to work together. The latter allows for applications composed of multiple tightly coupled containers that share resources. Some pods may also have init containers that run before app containers and sidecar containers that provide additional services to the main application. In Kubernetes v1.29 beta, the sidecar containers feature gate is enabled by default, allowing for the specification of restart policy, always for init containers. This ensures that containers defined as sidecar containers remain running throughout the entire lifetime of the pod, starting before the main application pod and shutting down with it. Container probes. Probes are periodic diagnostics performed by the kubelet on a container, which can include exec action, TCP socket action, and HTTP GET action. Exec action is performed with the container runtime, while TCP socket action and HTTP GET action are checked directly by the kubelet. More information about probes can be found in the pod lifecycle documentation.